Okay, guys, today we're doing the second last lesson of this chapter, which is solubility. We're going to be going over a couple definitions to start with. Then we're going to get into how different factors affect solubility. We're going to be using a solubility table, which you have on the back of your formula sheet, in order to predict whether something is going to dissolve or become a precipitate. Then we're going to look at different types of solutions and how dynamic equilibrium affects the dissolving process. So solubility, our first definition. So solubility is just the amount or the mass of a solute that can be dissolved in a given amount or volume of solvent. So essentially, how much stuff can you dissolve in how much stuff? We can also look at solubility of being the concentration of a saturated solution. We'll talk about what a saturated solution is later on in this lesson. The most common unit that we measure solubility in is grams per 100 milliliters. So essentially, how many grams of something can we dissolve in 100 milliliters of our solvent? If you have a really high number for your solubility, that means that the substance dissolves really well. A low number would mean that it's not very soluble. If something does dissolve at all, it's considered soluble. The term miscible is another way that we describe how well two different substances mix. If two substances can mix in all proportions, they are considered miscible. So if I can take any amount of a solute and dissolve it in any amount of a solvent, then it's miscible. If substances don't mix, but instead form layers on top of each other, like say oil floating on top of water, then those are called immiscible. Usually it's when we have a polar and a non-polar substance that we're trying to mix together. If you remember, like dissolves like. So if you have two unlike substances, they're not going to dissolve very well. So if we think of oil and water, we have oil, which is non-polar, floating on top of water, which is polar. They're immiscible because they're unlike. Temperature, oh, sorry, that's the doorbell. Temperature will affect solubility. Essentially, the warmer it gets, the more soluble most solids will be in different liquids. So if you mix, like, if you're making like hot chocolate with powder or something like that, the warmer your water is, the more of that chocolate mix powder you can dissolve in. That's why when you start drinking your hot chocolate, it might seem like everything is dissolved in it. And then as your hot chocolate cools, the solubility of that powder decreases. And so some of that powder will fall out of the solution, and that's why you get all the chunk at the bottom. As temperature increases, the solubility of gases in liquids decreases though. Those of you that were in Bio 20 will remember that the warmer water gets, the less oxygen it can dissolve. And that's true for all gases in all liquids. The warmer it is, the less gas can be dissolved in the liquid. So temperature has opposite effects on solids and gases when we're dissolving them in liquids. Liquids dissolved in liquids, not at all affected by temperature. Pressure can also affect solubility, especially when our solute is a gas. The more pressure you put on that gas, the more it will dissolve in solution. This is why a pressurized bottle of Coke or something will have lots of carbon dioxide dissolved in the liquid, and as soon as we release that pressure by opening the bottle, the carbon dioxide comes out of the solution, because with the lower pressure, it's not as soluble. Ionic compounds are soluble to some extent in water because the polar ends of the water molecule will pull apart and have an attractive force on our ions. But not all ions are equally soluble. Some of them will be very soluble, meaning they dissolve really well in water, and some of them will be only slightly soluble, which means they'll dissolve a little bit, but not a lot. And we use solubility tables to tell us which ionic compounds are going to be very soluble and which ones are only going to be slightly soluble. The slightly soluble ones, again, will dissolve a bit, but most of that solute won't dissolve. And instead, it becomes a precipitate, which is a solid that forms during a displacement reaction. So the precipitate that forms either has to be completely insoluble or only slightly soluble. So this is what a solubility table looks like. Over on the side here, this says very soluble. So this is going to be things that dissolve really well. Below that, it says slightly soluble. So that's stuff that's not going to dissolve very well and will probably form a precipitate. So the way that we use this is, say you had something like sodium hydroxide, NaOH. I would find my non-metal or non-metals first. So in NaOH, the OH is the non-metal. So I find my non-metal across the top. So right here is the OH. And then I look underneath that in the white part to find where the metal is. So in this case, the sodium, the Na. Now, because sodium is a group 1 metal, meaning it is in the first column of your periodic table, then we're looking at something in the top row of that white section of this chart. And anything that falls in the top row is very soluble, so it will dissolve. On the other hand, if I was looking at magnesium hydroxide, my hydroxide is still in the same place, obviously. And then if I'm looking for magnesium, it's not a group 1 element. Magnesium is a group 2 element. It's not one of the compounds listed here. And so instead it falls into that most category, where most metals will fall. And so because it's in that bottom section, it is only slightly soluble, therefore it will be a precipitate. Okay? So anything that's in the bottom is a precipitate. Anything that's in that top section will dissolve, it's soluble. So aqueous reactions are just reactions that take place in water, and a lot of displacement reactions have to take place in water. Again, the water is not a reactant, it's just the required environment for the ions to react with each other. So we will take 2 ionic substances, or 1 ionic substance and a metal usually, and allow them to react in displacement reactions. In those displacement reactions, the metals will switch places with each other usually. You can also have displacement reactions where the non-metals swap places, but essentially you have to have like elements swapping places. So I'm going to stop here and allow you to try and predict the solubility of these different compounds. So tell me which one will be soluble and which one will be insoluble using your solubility table. Okay. And then in the reactions below that, I want you to tell me which one of those products would be a precipitate. So pause here if you want to try it on your own, or keep watching and I'll show you how to solve this. Okay. Let me just go down to my paper. Okay. I want this to be upside down for you, but Okay, so the first question asked us to compare these in terms of solubility and figure out which one is more soluble. So the way we do that is we look at our solubility table here, and first we'll find AgCl. So we always find our nonmetal, which is our chlorine, across the top. So our chlorine is right here. And then we'll look underneath and find silver Ag. And since it's down here, that means it's only slightly soluble. So this one is only slightly soluble. Then we'll look at our AuCl. So once again, we find our chlorine, our nonmetal, across the top first. And then we look under it to find our Au. Now, since Au is not listed down here, it falls into the most category, therefore is very soluble. Again, pause here if you want to try the second one on your own and you haven't yet. So once again, with magnesium sulfide, we find the nonmetal across the top. So in that case, it is our sulfur. And then we look underneath it to see where magnesium is. Now, magnesium is a group 2 element, so it falls into the top here and is therefore very soluble. Our other one, aluminum sulfide, because aluminum is not group 1 or group 2, it falls into the most category and therefore is only slightly soluble. Now, in cases like this where we have a reaction and it's asking us to predict which of the products is a precipitate, we have to start by writing out our double displacement reaction. So right now we are going to take our two metals, mercury and potassium, and swap them places. So I will end up with KNO3 and HGBr. Okay. Then I'm going to look at my solubility table and see which of these is very soluble and which is only slightly soluble. So again, I'm going to start by finding my nonmetal across the top. So my NO3 is right here. And then I'm going to look for potassium underneath that. And because this says all, that means that all metals mixed with any of these are very soluble. So this is very soluble. We'll do the same thing with our mercury bromide. So we'll look for our bromine across the top first, and it's right here. And then we look for Hg underneath that. And because it's right here, that means it's only slightly soluble, which means this is our precipitate. It's only slightly soluble. It's not going to dissolve very well. Instead, it will precipitate out. Okay, again, stop here if you want to try the second one on your own, which you should do if you haven't already. Okay, again, to do the double displacement here, I'm going to take my two metals and swap them places. So I will end up with MgOH and NaS. Don't forget to cross over your charges. So magnesium has a charge of 2, so I got to put my OH in brackets and put the 2 outside. OH has a charge of -1, so we don't bother writing it in. Sulfur has a charge of 2, sodium has a charge of 1. So it would look like that. It's not balanced, that's fine. It doesn't need to be in order to identify our precipitate. So once again, I'm going to start by finding my non-metal across the top. So OH is right here. And then I'm going to look for my magnesium. Magnesium is not a group 1, nor is it any of these, so it falls into the most category. It's only slightly soluble. That is going to be a precipitate. We'll check our sodium sulfide as well. We'll find our sulfur across the top. Sodium is a group 1 element and therefore very soluble. It will dissolve. Okay, so that's how we solve that kind of problem. Okay, so moving on to dissociation reactions. So we've looked at dissociation reactions already, where we have just a single ionic compound breaking apart into its ions. But we can also write dissociation reactions for essentially double displacements like this, or even single displacements, where anything that will dissolve, any of our products that will dissolve, need to be broken apart into those ions, and only the precipitates will remain as whole compounds because they don't dissolve. So I'm going to walk you through how to essentially write this type of dissociation reaction. Okay. Hopefully you can see me on this little camera over here as we follow along with these steps. So this is a dissociation reaction. Okay, so the way that this is going to work is I'm going to start by writing out my two reactants. So I have sodium sulfide and nickel sulfate. You do not have to know the name of sulfate at this point. And it tells us here that nickel has a charge of 2. So we're going to start by writing out our double displacement reaction. Again, we're going to take our two metals and swap them places. So I end up with nickel sulfide and sodium sulfate. Okay. I can tell that sulfate has a charge of 2 because in our original reactant, we're told that nickel has a charge of 2. So it must have got canceled out. So we'll put a little 2 in there. What I'm going to do next is look at my solubility table and see which, if any, of my products are precipitates. Okay. So let me just switch back to my camera for a second. And here we go. Okay. So I was given my two reactants. I have done my double displacement, switched my metals, end up with these products. I'm now going to find my non-metal on the top of my solubility table, and then I'm going to look for nickel underneath. Now, nickel is not group 1 or group 2, so it falls into the most category. So down here is, again, our slightly soluble. So this is definitely going to be a precipitate. Then we're going to find our SO4, our nonmetal. So SO4 is right here. And sodium is not in this list, so it falls into the most category, meaning it's going to be very soluble. So it is going to dissolve. And so our next step, you can see it under here. Oh. Our next step is going to be to rewrite the chemical equation, but any non-precipitate products must be written as individual ions, and then we balance it. So essentially, this product can stay as it is, our precipitate can stay as it is, but our very soluble compound has to dissociate. So we will rewrite it like so. With our very soluble product breaking apart into its two ions. And then I just balance it by putting a 2 in there, okay, because I have 2 sodiums on the other side. And that's it. That's how you do that kind of problem. What I would like you guys to do now is to try this problem. Okay, writing the dissociation reaction for the reaction between calcium hydroxide and sodium sulfate, and it shows you what sulfate looks like, including its charge. Okay, pause here and try that problem, and then unpause, and I will show you how to solve it. Okay, so the problem is asking for the reaction between calcium hydroxide, oopsies, there we go, calcium hydroxide and sodium sulfate. So sodium sulfate, and it told us what sulfate looked like and that it had a charge of -2, so we'll cross that over. Don't forget to cross your charges over here as well. Calcium has a charge of +2, so we'll put our OH in brackets and cross over our 2. Then we have to write our double displacement. So we're going to take our metals and swap them places. So we will end up with calcium sulfate and sodium hydroxide. Calcium and sulfate both have charges of -2, so they cancel out. That's a 4, by the way. And sodium and hydroxide both have charges of 1, so those will cancel out. Okay. So it'll look like that. That's step 1, is just to write it out. Step 2, use our solubility table to figure out which of these, if either, is a precipitate. So we'll start by finding our SO4 across the top. It's right here. And then we're going to be looking for calcium underneath it. So calcium is down here. Anything in the bottom section is a precipitate. So that is definitely a precipitate. Then we'll go over to our other compound. We have OH here. Sodium is a group 1 element. Anything that falls in that top column is very soluble. So it's going to dissolve. Now we have to rewrite this. Our precipitate stays as a compound. Our very soluble compound, the one that's going to dissolve, has to be broken apart into individual ions. Okay, so don't forget, anything with an ion must have a charge. OH has a charge of -1. And then we have to balance this. So I'm going to put a 2 here and a 2 here, because this tells me that I have 2 OH and this tells me I have 2 sodium. And then that's the final answer. Okay, next up we have our definitions of different types of solutions. So an unsaturated solution is a solution that could dissolve more solute at whatever temperature that it's at. There won't be any undissolved solute floating around or at the bottom. Everything is completely dissolved that's in there, and it could dissolve more. That is an unsaturated solution. A saturated solution can't hold any more solute. It has the maximum amount of solute already dissolved in it for whatever temperature it's at. All saturated solutions will contain both dissolved and undissolved solute. So you will see some undissolved solute floating around or sitting at the bottom, because the only way that you can tell that a substance or a solution can't hold any more solute is to fill it with as much solute as possible and then see that some of it's not dissolving. If something is at dynamic equilibrium, it must be a saturated solution. All saturated solutions are in a state of dynamic equilibrium, which means that the rate of dissolving is equal to the rate of crystallization or precipitation, which is essentially the opposite of dissolving. So all saturated solutions have this continual process of some of the solute that is like sitting at the bottom dissolving into the solution. At the same time, that some of the solute in the solution precipitates out or crystallizes out. Okay? So the amount of solute that is dissolved doesn't change, but there's constantly dissolving happening at the same rate that crystallization happens. We can also have something called supersaturated solutions, which can occur under very specific conditions. Essentially, it means that for a short period of time, that solution has more solute dissolved in it than what it should be able to hold. Usually what happens in order to create a supersaturated solution is that you heat up the solution, dissolve a bunch of solute in it, and then cool it down very rapidly. And during that cooling process, it will be supersaturated until some of that extra solute has time to crystallize out. Okay, this works because as temperature increases, you can dissolve more of a solid solute into a liquid. So when you increase the solution's temperature, you also increase the solubility of the solute, so you can dissolve more solute in it when it's warmer. And then as you cool it down really quickly, the solute can't precipitate out as fast as the temperature drops. So it is temporarily supersaturated until the solute crystallizes out. Okay, I'm going to give you some time, or take some time, pause the video now, to read over this question, see if you can solve it, and then I'm going to go through the explanation of it. Okay? Okay, so when it says how much do we expect the salt to weigh, assuming the container was sealed, the answer to that is that we expect it to weigh 15 grams. Because we started with 15 grams and the solution was already saturated, that means that none of that 15 grams of salt that we added were able to dissolve because the solution could not hold any more solute. So we would expect that it would remain at 15 grams. Now, if the container wasn't sealed, we would expect our final mass to be greater than 15 grams. We don't know exactly how much it would be, but it would be more than 15 grams. And the reason for that is that if the container wasn't sealed, some of the water in the container would evaporate, meaning that we would have less solution over time. And if there's less solution, that means that it can hold less of the solute. And so as the water evaporates, the salt would crystallize out and be left behind. So we would end up with more than the 15 grams that we put in because you'd have some evaporation of water. And then lastly, why did the salt break down into chunks? Well, that has to do with the fact that you have dynamic equilibrium happening. So if I have a beaker or a container of some sort, and I have a solid chunk of salt or whatever that I've placed in the bottom, and then we also have salt particles that are dissolved in the solution. Because we have dynamic equilibrium, some of this solid salt would dissolve into the solution, and some of this dissolved salt would crystallize out and would just form a little chunk at the bottom. And so over time, as that continues to happen, it would look like our hunk of salt is breaking down because it is in fact dissolving, and then the salt that was in solution is crystallizing out, but it's not reforming a solid chunk. Okay, it's breaking down into smaller little chunks. Okay, so it all comes down to dynamic equilibrium. Okay, guys, and that is it. That is all of solubility. Let me know if you have any questions. Feel free to email me. And yeah, hopefully this worked out okay.